Hey, I thought we could sit here and go through the homework together just to make sure we try to understand it as best we can. So let's just hop into it again. We're in 10.3 and we're looking at the following. All right, so if we just kick it off with number 1 here, let's see. It says to determine the critical value for a right-tailed test where, of a population mean where alpha is 0.01 and the degrees of freedom equals 15. All right. So if we pull up our chart, all right, so let me add a little picture in here. Let's see. And let me see if I can just make this thing bigger. Yeah. So for here, our degrees of freedom is 15. So we're looking at this particular row right there. Right? And alpha equals 0.01, which is this column right here. So if we kind of blow that up a little bit and see where they meet, looks like it is right there. Right. So here, my t statistic is 2.602. Okay. Let's see, for part B, all right, we're given alpha equals 0.05. Right? And this is a left-handed tail test. Right? So again, for part 1, this was my t-score of 2.602, or for part A. So for part B, this is a left-handed test right here. So this should be a negative number when we get done with it. Right? So here we want alpha to be 0.05, n equals 20, which means our degrees of freedom is 19. Right? So for this one, go down to row 19 right there. Alpha equals 0.05 is this column right there. So again, if we blow this up, it looks like I have a t-score right there of 1.729. Right? But since this is on the left-hand side, we'll make that a negative 1.729. Right? And then for part C, so let me write it up here. 1.729. For part C, we do this. We have a two-tailed test, right, which means when we get our t-scores, right, we'll have the negative t-score and we'll have the positive t-score. Right? So for part C, alpha is 0.05, n is 13, which means my degrees of freedom is 12. So for this one, degrees of freedom is 12. Alpha is 0.05. So again, if we blow this up, it looks like I get 1.782. So let me move that over here a little bit. So that's this t-score, 1.782. So this t-score would be a negative 1.782. Let's see. Oh, no, wait a minute. I messed up on that one, right? Because I forgot, let me undo that. I forgot this was a two-tailed test, right? So since it's a two-tailed test, when I add this part together and that part together, I want that to be 5%, which means this is 2.5% and this is 2.5%. So what I'm looking up here is actually this column 0.025 right here, right? So it looks like it's going to be this particular number then, which is 2. Let's see. Oh, sorry, right here. It was on the wrong level. 2.179. Right. So that t-score should be 2.179. That t-score is negative 2.179. Yeah, so remember for the two-tailed tests, break up that probability into those two tails. Okay. All right, so there's number 1. All right. Let's flip on to number 3. All right. So for number 3, we're testing this null hypothesis, this alternative hypothesis. All right, so it's a one-tailed test here. A simple random sample of n equals 24, right, is obtained from a population that's normal, right? And again, remember that's good because if it's not normal, we need sample sizes of at least 30, right? And we are told that, excuse me, X bar is 47.1, the standard deviation from the sample is 10.3, so we need to calculate this test statistic, right, which is, again, X bar minus mu over the S over the square root of n. So X bar, again, is the number that comes from the sample, mu is the claim, S is 10.3, and I took a sample size 24. And I get negative 1.379. Okay. All right, so that's our test statistic for number 3. Right? So for part B, the researcher decides to do this hypothesis test at alpha equals 5%, so 0.05. Right? Let's see. We want to draw a t-distribution. Right? So I want this t-distribution. There's this t-score of negative 1.379. Right there. And are we going to accept or reject the null hypothesis? Well, again, let's pull open our chart and see what we're going to have here. So let me add this photo again. Right here. All right. So in this case, if you remember, let's go back a page here. Let's see, n is 24, which means the degrees of freedom is going to be 23, and my test statistic was negative 1.379, but this only has positive t-scores in our chart. So what I can do is I can look up 1.379, and the chart will give me the area to the right of that number, and since it's symmetric, this area is going to be the same thing as that answer right there. So let's see what number pops up for this p-value. So let's see, so degrees of freedom is 23, which is this row right here, right? And I am looking for 1.379. So again, if I can blow this up a little bit, 1.379 looks like it falls between these two scores right here, right? Which means the p-value falls between those two scores right there. So for this particular problem, the p-value is between 0.05 and 0.10. So let's go back and write this down. All right. So if my p-value is between 0.05 and 0.10, that means the p-value is bigger than alpha. And if you remember, when your p-value is larger than alpha, we do not reject the null hypothesis. Okay. So that is number 3. Right? Let's jump into number 5. I might need this later, so let me clean this part up a little bit. So for number 5, we've got this hypothesis test. Mu is 100 versus a two-tailed test that mu is not 100. Right? We're taking a simple random sample of size 23. Again, the population is, we're told to be normal, which is good, because again, if it's not normal, we can't do any of this stuff unless we have samples of size 30 or more. We're told that X bar is 104.8. The standard deviation is 9.2. So the first thing we're asked to calculate is our test statistic T naught. So it is X bar minus the mean over S divided by the square root of your sample size, and that gives me a t-score of 2.502. Okay. Let's see, in this case we're going to test it at alpha equals 0.01 at that level of significance. Right? So for the t-distribution, remember in the t-distribution the average is always right there at 0. So we've got a t-score here of 2.502. So what we're going to do, since this is a two-tailed test, I'm going to find this area, and then I'll come down here to t equals negative 2.502, and since it's symmetric, this will be the same number, but I will add these two together, right, to get my grand p-value, my total p-value. Okay. All right, so should we accept or reject? Well, let's look this one up in our chart to see what's going to happen. Right. So n is 23, so my degrees of freedom is 22. So let's go back to our chart. Let's see, so right here, I have 22 as my degrees of freedom, and I was looking for a t-score of 2.502. So if we blow this up, 2.502 falls between these two scores right here, where if we look up at the top here at the p-values is right there. So in this case, I know that the p-value is between 0.01 and 0.02. Okay. Let's see. All right, so if we go back to this chart, or this work we were doing before, right, the p-value for that one area is between 0.01 and 0.02, so if we multiply it by 2 to add them both together, this is my grand total. Right. Okay, sorry, I went back to the wrong page here. Let me get rid of this and go back to the right one. Yeah, so here it was between 0.01 and 0.02. So then when I add it to this one, or multiply it by 2, I get the p-value is between 0.02 and 0.04. Okay? Now, how does that compare to alpha? Well, the p-value is going to be bigger than alpha, so that tells me that I do not reject here. Sorry, I was flipping back and forth between the wrong pages there. All right, so again, that's number 5. So for a two-tailed test, you find one of the probabilities using the chart, and then you can just multiply it by 2 to get the other one. Right? And the charts are set up to use these positive t-scores, not the negative ones. All right, let's keep on rolling. Let's go to number 9. Right. For number 9, let's see, we've got this test. The null hypothesis, or the claim, is that mu should be 105 for something that we're testing. The alternative hypothesis is that mu is not 105. Right? A simple random sample of the size 35 is chosen, and in this case, we don't know if it's normal or not, the original population. Right? So again, here's our population. We have no clue if it's normal or not, but since our sample size is bigger than or equal to 30, we know that we can use our normal stuff and our t-distribution stuff. Okay? All right, so that answers actually part A. Does the population have to be normal? No, because we have a large enough sample size of at least 30. Right? So we're also told that the average from this sample is 101.9, the standard deviation from this sample is 5.9, and we want to calculate our test statistic t. So again, it's the sample average minus the claim over the standard deviation divided by the square root of the sample size. Right? So that gives me a t-score of negative 3.108. All right, so this is a two-tailed test. Right? So I want to find the p-value from this particular t-score. From its positive counterpart, add them together, and that gives me my grand total for the p-value. Okay. All right, so let's look at our chart, right? And then in this case, the degrees of freedom is going to be 34, and I want a t-score of 3.108. So let's look at our chart again. So let me erase some of the stuff that we were using before. All right, so for this one, 34 degrees of freedom, right? And I'm looking for that t-score of 3.108, which, if you notice, falls between these two numbers right here, where if we go back up top, that gives me these p-values, right? So 0.0025 is less than p is less than 0.001. All right, so now let's take this p-value and go back to our problem, assuming I picked the right one here. So 0.0025, did I pick that right? Yeah. And, whoops, just kidding, is less than p is less than 0.001. But again, that's just the p-value for this part. So if I add it to this one right here by multiplying it by 2, I get 0.005 is less than p is less than 0.002. Right? So I know my p-value is somewhere in this region. And when I compare that to alpha, which in this particular problem for number 9, we're told alpha equals 0.01. Okay? So this p-value is smaller than alpha, which means we reject the null hypothesis. All right. So there's number 9. Let's see. Number 11, right? This is where now we have to start thinking about how to set these up on our own, right? According to an ATM network, the mean ATM withdrawal is $67. So that's the claim here, that mu should be 67. Okay. Let's see, payees manufactures an ATM that allows one to pay bills and so on, as well as withdraw money. A review of 40 withdrawals, so I'm taking a sample of size 40, so I don't care if the population's normal or not, shows that the mean withdrawal is $73. So in this case, the average from the sample was 73, right? So then how do we set up the null hypothesis? Well, let's read what it says. The question they're asking is, do people withdraw more money? In other words, based on this sample, they think people are pulling out more than just $67. So they think that mu should be bigger than 67. All right, so they're thinking this is a one-tailed test. Okay. All right, so for part B, we are told that they did the work and got a p-value of 0.02. All right, and asked us to explain what this means. This means that, again, remember 0.02 is the same thing as 2%. So what this means is that if their claim is true, this sample would only happen 2% of the time, which is 1 out of 50 times. Okay? So if we're testing alpha equals 0.05, what that means is if there's enough evidence to say that something happens less than 5% of the time, we reject the null hypothesis. If there's not, then we don't reject it. So since this sample happens 2% of the time, this tells me that since alpha is 0.05, I should reject the null hypothesis. Right. So again, this hypothesis testing is trying to find evidence to reject the null hypothesis. So what we're saying here is that this p-value, which again is the probability that the sample happens, this p-value is so small that it really shouldn't happen, which means if your claim is right, this sample shouldn't occur. Therefore, we think your claim is wrong. Okay. So that's how we can get through number 11. So for part C, when it says to write a conclusion, our conclusion would be that because the probability of the sample is so small, we will reject the null hypothesis in favor of the alternative hypothesis. All right, let's go on. Let's look at 14. All right. For 14, we're looking at an SAT verbal score. All right, it says, do students learn English as well as another language simultaneously score worse on the ACT reading part? Okay. Let's see. The mean score among all test takers on the SAT critical reading exam is 501. Right? So here, we're saying the mean is 501. Okay? A random sample of 100 tests, right? So again, I don't care if the population is normal since that's bigger than 30, found that the average in that sample was 485. Okay? Let's see. And the standard deviation, from that sample is, let's see, they told us 116. Okay. All right. So the question is this: do these results suggest that students who learn English as well as another language simultaneously score worse? Right. In other words, should the mean actually be worse than that? So should it be less than 501? Right. So again, this is another one-tailed test. Okay. So let's get our test statistic for 14. Right. So here T is going to be the average from the sample minus the claim over the standard deviation of the sample over the square root of the sample size. So this is going to give me a t-score of negative 1.379. Right? So again, here's what our t-distribution would look like. The average occurs right there at 0. Here's my t-score of negative 1.379. I want to find this probability. But again, the way the charts are set up, I will find the positive t-score, and it gives me this area right here, which, since it's symmetric, is the exact same value as that one. So let's see if we can find this particular p-value. All right, so for this case, let's go to our charts and see if we can kind of figure out what's going on with this. All right, so let me erase some of this stuff here, here, and here. All right. So in this case, I have a sample of size 100. I don't have one for 99, so let's go ahead and use this particular line right there. All right. I got a t-score of 1.379. So if we go along this row, it looks like it's between these two values right here. So if we go all the way back up to the top, it's between these two values right here. So in this case, the p-value is between 0.05 and 0.10. Okay. So this p-value is between 0.05 and 0.10, which means so is this one. Right. So for 14, let's see. If we let alpha be 0.1, okay, how does alpha compare to my p-value? Right? Well, p is somewhere between 0.05 and 0.10, which means the p-value is smaller than alpha, which means we reject the null hypothesis. All right, just a few more to go here. Let's look at 19. For 19, let's see, the age of death row inmates. Let's see, according to their claim, the average age of death row inmates was 40.7 years. So sociologists wonder if the mean has changed since then. So the null hypothesis here is that the mean is just going to be different from 40.7. Okay. Let's see, they take a random selection of 32 inmates, right? So again, it's bigger than 30, so I don't care if it's normal or not. The average from the sample was 38.9. The standard deviation from the sample was 9.6. And for this one, we're going to do a two-tailed test by creating a confidence interval. Right? Because remember, the idea is let's make a confidence interval. If their claim falls inside this confidence interval, we don't reject it. If their claim falls outside that confidence interval, then we do reject it. Okay? So let's see if we can construct this thing. All right, so this kind of relates back to what we're doing in section 9.2, where to make this confidence interval, we took x bar and we add and subtracted the t-score of alpha over 2 times s over the square root of n. Okay? All right, so for this particular problem in 19, we're trying to make a 95% confidence interval, which means alpha is 5%, right? So alpha over 2 is 2.5%, which is 0.025. Okay. All right, so here's what we've got. To create my confidence interval, x bar is 38.9. S, the sample standard deviation is 9.6. N, the size of the sample is square root of 32. Right? Now, what's my t-score going to be? Right? Well, I know if n is 32, my degrees of freedom is 31. Right? So if we look at our chart, let me again erase some of our previous work here. I'm looking at a sample of size 31. Right? In this case, alpha is 0.025, which is right here. So the t-score that we want is this one right there, which looks like 2.040. So this t-score is 2.040. Okay. So if we multiply all this stuff together, here's what we get. We get 38.9 plus or minus 3.462. Right? So if we add those together, we get 42.362. That's my upper bound. And then if we subtract them from each other, we get 35.438. Okay, so now, let's see, what number was this one? 19. Let me go back and read through this. All right, so for this one, since the mean, 40.7, this number right here, falls inside my confidence interval, that means we do not reject H0. Okay. All right, two more. Let's see here. So here's number 23. For 23, we have to do a little bit of work. All right, so for 23, we're given this setup, right? Calcium is essential to tree growth. So, all right, so let's see. In 1990, the concentration of calcium in participation was 11 or 0.1111 milligrams per liter, right? So in this case, I have H0 is that mu equals 0.011, right? They take a random sample of size 10, and what we're going to have to do is we're going to have to calculate the average and standard deviation by hand, right? And when you do that for 23, here's what you get. All right, so we get the average in this particular sample is 0.1568, and the standard deviation in the sample is 0.0867. All right, so let's see what else we can get from the question. It says, because the sample is small, we must verify the calcium concentrations are normal. We're not going to do that, so let's just assume that they are normal. And then in part C, it says, does the sample evidence suggest the calcium concentration has changed? So they're not saying bigger or smaller, just changed. So in this case, it's going to be the mean is not 0.011. Okay? So what we want to do is test this at the level of alpha equals 0.05. Right? So what we need to do is to get our t-score, right? And then the negative of that t-score, right? Add these two areas up and then compare it to alpha. Right? So in this case, my test statistic is x bar, 0.1568, minus their claim, which is, I wrote that down a little bit off. It's 0.11, not 0.011. Right, so it's 0.11 over the standard deviation S, which is 0.0867, over the square root of the sample size. Right? And that gives me a test statistic of 1.707. Okay, so that's this t-score. So the negative would be a negative 1.707. Again, let's look this up on our charts where since n is 10, I know the degrees of freedom is going to be 9. So let's go to that particular line. Let's see here. So let me go to this. All right. So my degrees of freedom is 9. My t-score was 1.707, which falls between these two scores. So the p-value falls between 0.05 and 0.10. All right, so this p-value is between 0.05 and 0.10, which means, since it's symmetric, same thing for this. So my total p-value should be 0.10 is less than p is less than 0.20. And when I compare this possible p-value to alpha, you can see it is larger than alpha, which means we do not reject the null hypothesis. Okay. All right, and then the last one, 27. For 27, what we're doing is we're referring back to number 23, which was a two-sided test. Right? So let's actually flip back to this one, right? And let's make our confidence interval here. So let me erase this stuff. So again, we got a p-value here between 0.10 less than p less than 0.20. Right. So for 27, let's just make our confidence interval, right, which again is x bar plus or minus my t-score times s over the square root of n. So in this case, let's see, x bar was 0.1568. All right, so my t-score of alpha over 2, alpha is 0.05, so I need to look up 0.025, and in this case I have 9 degrees of freedom. So if we look that up on our chart, let me go back to here and erase this stuff. All right, there is 0.025, whoops, just kidding, that's 0.25. 0.025 is right here. So if we go down to 9 degrees of freedom, there's the t-score that we need, 2.262. So let's go back up here and plug that in for this particular t-score. Right? S was 0.0867 and N was 10. Right? So this is 0.1568 plus or minus, let's see, and you multiply all this stuff together, gives you 0.0620 is what it rounds up to. Right? So to get my upper bound, let's just add these together, which gives me 0.2188. And if I subtract them, you get 0.0948. Right? So this is a 95% confidence interval. Right? And if you notice, mu 0.11 is in there, which would mean that we do not reject the null hypothesis. Okay. Now, some of you eagle-eyed viewers out there might look at this problem and say, well, the book says let's test it at the 99% level. Okay, let's see what happens there. So when I make a 99% confidence interval, what's going to happen? Well, if you remember, if this is a 95% confidence interval, a 99% will give me even bigger bounds, right? Which means 0.11 is still going to be in there, right? So we can do the work if you want to, get a different t-score, but even though I kind of muffed it up a little bit, I know at the 99% level, it's also going to not reject the null hypothesis. Okay. All right, so that's our homework set. Hope it helped out. Talk to you later. Bye.